Eyesight. Of all our senses, vision is the one we rely on most for our very survival. Many other species survive and prosper by their ability to see outside human limits.
Animals are very clever in their sensing capabilities. They have a lot to teach us.
Technology is creating robots which see more efficiently than humans. Can technology learn to see by itself?
In the case of an infrared telescope, we're seeing in a different way. We're making artificial eyes that give us an entirely different view of the universe.
How will the world look when we see like snakes, or dolphins, or the birds and the bees?
The more we look at them, the more we find that they're not that different from humans. And the question we really got to ask ourselves is, what are we doing with a brain as big as this?
Wild Tech explores seeing. If technology can learn from nature, sometimes the lesson is that the simplest things teach the most. When it comes to seeing, scientists are realizing insects may hold the clue to developing independent seeing machines.
Insects are quite different than mammals in that their brains are very small compared to even the smallest mammal, with very few neurons. Instead of billions, as in the case of our brain, they have tens of thousands. The insects, say, ranging from a housefly with 50,000 neurons to a honeybee with 1 million neurons. It's obviously a much simpler system. And also they've been flying around for a very long time, something like 320 million years. So for all of that time, they've been evolving these very small, robust visual systems. So it's very appealing to think about trying to reverse engineer them. Okay, let's check the sensors.
Each plane is fitted with standard movement sensors, which indicate the pitch, roll, and yaw of the plane.
That's a good signal. Okay, let's check the optic flow.
What's unique is a nose camera, which controls the plane's flight not so much by what it sees, but by determining how fast it's moving through the landscape.
Well, the technology is an attempt to reverse engineer insects' nervous systems and vision systems. And what's a bit unusual is that rather than take a hardcore engineering approach where we start from first principles with a blank sheet of paper, we've used an example from nature which we know works to try to get a good outcome. And we're starting to see results from the approach.
To fly like a bee, you need to see like a bee.
Bees' eyes are compound eyes. That means they have many, many little eyes. But that difference is really not a dramatic difference. One of the big differences is that bees don't have stereo vision because the two eyes are very close together, and so that makes stereo very difficult for them. So they use motion cues a lot more than we do. So that's one difference. The other difference is that bees don't see very sharply. They don't see as much detail in the world as we do, but they see changes very well. So they would see, for example, the flicker in a movie, which we wouldn't, but they would see the flicker in a fluorescent lamp, which we wouldn't. So the world is a lot blurry, but a lot faster.
Dr. Srinivasan has developed an elaborate test to determine how bees see the world and how they use their sight to navigate, judge distance, and execute smooth landings.
So bees enter this tunnel, as you see here. They fly along the tunnel all the way to the end, and they settle down on this feeder, which gives them a nice feed of sugar water, which they like, and then they fly back all the way along the tunnel to the end and then back to the hive. Now, the purpose of this experiment is to try and work out how bees control their flight speed when they fly. And we do this by moving the tunnel walls and working out how these bees react when they see this motion. It turns out that bees cannot really know how fast they're flying until they refer it to how the environment appears to be moving on the eye. So it looks like what they're doing is regulating the flight speed based on how rapidly the world appears to be moving past them. So if you bring them into a narrow gap, they will slow down. If you make them fly in a wider gap, they will speed up.
When the background dots move in the opposite direction to the bees, their eyes tell them they are traveling fast, so they slow down. When the dots move in the same direction as the bees, their eyes tell them they are barely moving, so they speed up. Humans in the same experiment would rely on the depth perception gained through stereo vision, and thus be able to move normally, assessing our speed and direction independently of the moving landscape.
So we're finding, for example, that bees have very simple, elegant ways of avoiding collisions with obstacles. They measure how rapidly something moves on the eye, and that tells them how far away the obstacle is. They can make very smooth landings on a horizontal surface, again by using a measure of how rapidly the ground appears to be moving beneath them. These ideas are very simple to put into aircraft and make them do things which we formerly thought impossible.
The biology of studying bee flight intrigued the U.S. Defense Department, which has already developed unmanned spy planes, like the Global Hawk, which is set on a predetermined flight path controlled remotely by computer. The Defense Department reasoned bee vision and its flight applications may be the simple seeing technique necessary to create truly autonomous aircraft.
So the input is in areas such as detecting obstacles and avoiding collisions with them, in making smooth landings, in following the terrain as the terrain goes up and down, in navigating through narrow gorges without colliding into the side walls, in stabilizing your roll and yaw and pitch. So all of these things insects seem to do using very quick, simple, shortcut solutions, which engineers normally don't think about. But by looking into biology, we get some inspiration.
Saul, are we getting an optic flow signal?
Yeah, it's looking pretty good.
Okay.
Scientists have taken the algorithms developed by bee research and applied them to the computer brains of model aircraft.
Okay, Dean, the plane's cocked and ready to go.
Testing is in its infancy. The planes are flown with remote control, and at a given moment, the pilot hands over the flying to the computer.
Okay, I'm going to hand over again. Yeah. So right here.
Yeah, that's a good signal.
Handing
there.
over. Whoa, 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 Jesus. What was it doing there?
Using onboard cameras, the computer sees the world zoom past and can assess its speed and position, avoid objects, and fly autonomously, just like the bee.
We're engaged with NASA in attempting to develop this technology far enough that we can put it into a mission that will land on Mars and launch these aircraft, and they'll fly across the surface gathering scientific data.
Autonomous probes have advantages over remote control probes for planetary exploration because of time delay. A remote control Mars explorer takes minutes to receive instructions from Earth and act on those instructions. If an Earth-controlled probe was heading toward a collision, the probe would crash before it could be told to stop or turn. A probe that could see like a bee would navigate autonomously, avoiding obstacles, landing on flat ground, exploring without hindrance. The way bees see will also aid navigation, because on Mars, there's no north or south, there's no GPS.
Other than optic flow, there are other interesting things that we can extract from insect behaviour. One of them is polarisation compassing. Insects, it turns out, don't prefer to use the position of the sun as their reference for direction. It seems that they actually use this distributed pattern that covers the whole sky, which is caused by scattering of sunlight from the direct line from the sun. That's very useful on Mars where there's no magnetic field, but it's also useful in the polar regions of Earth.
Bees definitely aren't silly as we think they are. In fact, the more we look at them, the more we find that they're not that different from humans. And the question we really got to ask ourselves is, what are we doing with a brain as big as this?
The simple way a bee sees may soon enable aircraft to navigate and land autonomously. Seeing beyond the realms of visible light will enable us to see to the beginning of time. Nature has evolved the ability to see outside the visible light spectrum. Birds of prey, like this sparrow hawk, have eyesight far superior to humans. It can see something the size of a softball a mile away. In human terms, it's like us being able to read a newspaper from 25 yards. Even with such impressive eyesight, this vole should be well hidden from the hawk's view. But it's not. The vole has made a fundamental behavioral error, which the hawk exploits with its advanced eyesight. Voles mark their trails with urine. This reflects ultraviolet light. Although outside our visible spectrum, the hawk can see the UV trail left by the vole as easily as we can follow the road to the supermarket. Astronomers are seeking ways to explore the universe through telescopes, which see outside the visible light spectrum. The Hubble Space Telescope exploits the same ultraviolet light the Hawk uses. The hottest and most active objects in space give off large amounts of UV. NASA's latest space telescope will be able to see even more than the Hubble. Maybe even to the dawn of time, exploiting another light frequency outside the visible spectrum, infrared.
T-minus 10, 9, 8, 7, 6, green board, 5, 4, 3, 2, main engine start, 0, and liftoff of the Delta II rocket with Certif, seeking hidden secrets in the evolution of our universe.
In the case of an infrared telescope, we're seeing in a different way. We're making artificial eyes that give us an entirely different view of the universe.
We've reached burnout on those solid motors. There's the air starts. All 3 air start motors are up and running.
The Space Infrared Telescope Facility, known as Certif, is the 4th and final of NASA's family of orbiting great observatories.
It's past T plus 100 seconds. Vehicle's now at an altitude of 18 nautical miles, downrange distance 40 miles, and a velocity of 37 miles per hour.
Certif will see the heat from distant objects in space, in some cases from bodies that are 13 billion light years away.
It's actually trying to detect heat light, what we call infrared light, from objects in space. And I always tell people, if you go outside on a warm day and close your eyes, and if you try to feel the warmth of the sun in the sky, you can feel it. You can actually feel warmth from the sun. But now go out at night, put your face up to the sky, and try to feel the warmth of the stars, or of galaxies very, very far away. You can't. There's no way that you can actually feel that heat. So our telescope has to be extremely cold in order to sense that heat coming from space.
Near freezing operating temperatures are vital to the integrity of the infrared technology.
The area of space right around the Earth and the Moon, like if we were to put Certif into orbit around the Earth, that's too warm. There's too much heat around there. So we've decided to kick Certif away from the Earth and let it just drift away into space over time. It'll end up falling into its own orbit around the Sun.
Like all telescopes, the better the optical performance, the better it sees. Operating at such extreme low temperatures gives science another opportunity to impress.
There's a mirror here, and in the case of Certif, it's not made of glass like most mirrors are. It's actually made of beryllium, because the curvature has to be absolutely perfect at extremely low temperatures. In fact, the neat thing about the mirror is that it's not the right curvature at room temperature. We've tested that. When we bring it down very, very cold, it snaps into a perfect shape.
Distant planets and galaxies take on a whole new look when viewed as heat images using infrared.
This is what you'd see if you had eyes like Certif pointed down at the Earth. Now, as you notice, you can't see any of the continents or oceans. One thing that you can see are dark swirls in the atmosphere. The dark swirls are caused by water vapor. Water vapor absorbs infrared, and so you can actually see where there are storm systems swirling around in our atmosphere.
With SuperSight from Certif, we'll soon be better understanding the biggest cosmic dramas which have been catching the attention of astronomers over recent years, using a unique way to peer through far-flung clouds like this, to witness the birth of a new solar system.
One of my absolute favorite pictures that the Hubble Space Telescope has taken is this one that we call the Pillars of Creation. What you're really looking at are giant dust clouds floating through space. And like we said, stars are formed inside these dust clouds. Parts of the dust cloud begins to collapse under gravity. Eventually, that brings together a star and an entirely new solar system. Now, the very smallest bumps that you're seeing there, the little bumps on the surface of the cloud, are about 4 billion miles across. That's roughly twice the size of our solar system, the Sun all the way out to the planet Pluto.
Certif may shed new light on the very structure of the universe.
There's a suggestion now that some of the dark matter that the microwave background tells us about is actually gravity coming from a parallel universe to us. An amazing idea. So I believe in my lifetime, or I really hope in my lifetime, we're going to get a better sense about what this higher nature of the universe really is. Telescopes like this are going to give us one step on that journey. The next ones will take us even farther. And I imagine in 50 years' time, we're going to have a much different view of what our place is in perhaps a structure of universes.
Infrared vision gives us the ability to see into deep space. Scientists are learning infrared has uses much closer to home. If only we could see like a pit viper. For the human hunter and animal hunter, vision is the primary sense. technology has allowed mankind to see outside the visible light spectrum. What we're only just discovering is that nature has been seeing the world through different eyes long before technology.
I was trained as an electrical engineer and an optical engineer, and that's where my expertise is. And when I look at the way the pit viper is put together, it amazes me how nature has been able to put this sensor together.
Dr. Masoud Motamedi of the University of Texas Medical Branch is studying one of the most remarkable seers of nature, the pit viper, a snake which views the world in a manner that is ingenious, and if these researchers discover how, could lead to breakthroughs in medical diagnosis and military applications. To see the world the way this snake sees it is truly remarkable.
All objects in the nature emit radiation. The color of that radiation depends on the temperature of the object. I'm emitting infrared radiation right now. Human eyes cannot detect infrared radiation. However, the pit viper can do that.
The snake sees heat. To human eyes, a rat is white and furry, but when the lights are dimmed, it disappears from sight. To the snake, it is always visible, regardless of time of day, standing out from the background heat.
The pit viper has some very distinct features. One is its ability to respond to a very small temperature. And by mean, I'm talking about a 3,000th of a degrees change that they're able to detect. And the other is the fact that they could detect these changes in a background temperature that could be very high or very low.
Okay, I'm seeing position and ID on everyone.
The military is the most extensive user of infrared technology. The ability to see in nighttime or murky conditions can mean the difference between your life or your enemy's. But the best machines cannot match the sensitivity of the pit viper. In addition, the electronics need to be kept at a very cold level with liquid nitrogen, so it can then detect heat elsewhere. The snake doesn't operate this way. It can sense the heat signals of prey regardless of its own temperature. Its accuracy of heat detection leaves technology in the cold.
About 5 years ago, we formed a consortium among 5 universities to respond to a call for proposal from the Department of Defense with the focus on understanding the mechanism of the pit viper infrared detection.
The snake doesn't use its eyes. It gets its name from the pits just below the eyes. This is one of nature's most finely tuned instruments, detecting radiation at minute levels. The pit membrane is 50 to 75 microns thick, around the same size as a piece of paper, and cooled by air on both sides. It is highly vascularized. This allows for quick dispersal of detected heat. Multiple nerves instantly transmit the heat detected from prey from the pit to the brain, where an accurate image is formed. Applying snake technology to human application is the challenge for the university team. Understanding mechanics is one thing. Now, the focus is on isolating the protein in the membrane neurons, which react to heat. By engineering these proteins, scientists are confident they can make highly robust and extraordinarily sensitive and cost-effective heat detection instruments.
We'll be able to see the
More importantly, they will not require artificial cooling.
Only those neurons will be able to.
It's not just military applications which can benefit from this science. Medical applications will revolutionize diagnosis and treatment of diseases.
Having a system that is highly sensitive to small changes in the temperature with a capability that could give high-resolution imaging may be very useful for cancer detection or detection of other diseases.
One application already underway is the detection of the dangerous plaque which causes heart attacks. It is known this plaque has a higher temperature than other plaque. A catheter tipped with the heat-detecting protein could be inserted directly into the veins.
One can decide whether this is a plaque that has a chance for rupturing and leading to heart attack versus a plaque that can be left untreated and not taking a big risk. It is incredible when you think about potential of a technology like this, that we have been only able to learn through what's out in the nature and what potential we can see for this.
Seeing through nature's eyes and extending our own vision capabilities. The next step in advanced sight may be to see like a bat. Robots can already see in a way similar to humans. Robots like COG of the Artificial Intelligence Lab at MIT.
Okay, COG, give it a bash. Okay, good shot. Now, let's see. You got this? You got this? You got this?
The human brain has evolved to work most effectively through visual stimuli, aided by sound. Understandably, robotics research tends to mimic humans, revealing just how complex the human animal is. COG learns to identify and move objects by a process of repetition, trial, and error. The next step is to then coordinate its robotic arms to anticipate how an object will move.
When we look at a simple animal, we find that it doesn't have heavy-duty cognitive processes going on inside. Well, some of them don't really even have heads. They've just got a few thousand neurons, perhaps, and there's no room in there to be doing really complex computations. There's no room in there to be building complete models inside their head of the world out there. You know, they don't have a 3D graphics picture inside their head. They're responding in much more direct ways. And by looking at animals and trying to analyze what cues they get from the environment, that gives us some real ideas on how we can build the robots and what the essence of the things that those animals are doing is.
While COG tries to mimic human sight to learn, some scientists believe that robot development would benefit from copying animals which see with sound. Specifically, the bat. It's hard to think of a more inaccurate expression than blind as a bat. While in human terms, it has bad eyesight, its ability to see with sonar is so developed, it can fly avoiding all obstacles in its flight path, regardless of the level of light, and identify a moth in 3 dimensions at 30 feet. Laboratory testing has shown that bats receive echoes back from objects much faster than their brains can process the information. The bat sends out sound pulses, and signals bounce back. The closer the object, the faster the echo. What's of interest to robotics researchers is that the bat broadcasts sound as high as 100,000 cycles per second. Yet its brain can process echoes at only 400 cycles per second. When flying through these wires, the bat sends out sounds, then receives back the echoes. Its brain is bombarded with rapid sounds to process, yet it slows the signals and reacts in time to fly through the obstacle course. It makes the seemingly impossible normal. The bat's ability to simplify the information it receives from its sonar and use it so effectively to navigate is of great interest to robot research.
Not too long ago, we developed a very sophisticated sonar that was able to tell the difference between the head and the tail side of a coin. But what happened in the end was that sonar was too complicated and also too expensive to be used in robots. We decided to use the sonars that are commonly used in robotics and explore their advantages. Animals are very clever in their sensing capabilities. They have a lot to teach us. My name is Roman Kutz. I'm a professor of electrical engineering at Yale University. And I'm investigating sonar signals that are used by bats to investigate their environment. I'm here in a cemetery to explore how naturally occurring objects produce echoes and how to extract information from those echoes that would be useful for bats to locate objects and navigate.
Cooch hopes to design for the visually impaired a wheelchair which can see where it's going, using sonar.
Most other experiments with sonar occur in a laboratory. In a laboratory, things have to be static and stationary. But what we're trying to do is discover what happens when a bat flies. So we thought of taking our experiment on the road, on this scooter that goes at a constant speed.
In this experiment, this man-made sonar is tuned to a particular speed to obtain spatial information from the environment as it moves along. In this case, certain plants in the garden are acting as markers.
When we pass a plant, we get a lot of different echoes. We're looking for echoes that have a particular form. They have to be strong, and they have to exhibit a particular time sequence. When that occurs, our sonar triggers and produces an identification pulse. And that permits us to identify landmarks.
This Batmobile will see like a bat by using sonar to recognize and steer around familiar objects, extracting a single reference point from a large number of echoes, rather than building a whole image. The hope is that a robotic vehicle will be able to self-navigate and retrace its path in the same way that a bat returns home to roost.
You really feel like when you develop these programs, that you're really seeing how the system evolves. You encounter problems, and then you try to fix them. And when you come up with a solution, you say, gee, that's the way biology must be able to solve these problems.
The way a bat sees through sound is clearly of interest to scientists working on other solutions for the blind. If the human brain can interpret changes in the pitch and volume of sound, sonar can, in effect, help the blind to see.
Oh, hello, Ivan. How are you?
Hello, indeed.
Fancy meeting you.
The thought came to me that maybe bats use a very wide bandwidth sonar system as compared with the simple pulses that we used to think bats transmitted.
Right.
Leslie Kay, Emeritus Professor at the University of Canterbury in New Zealand, has spent nearly half his life developing sonar systems to help the visually impaired to see using sound. The latest development, CASPRA, or Kay's Audio Spatial Perception Aid, is on the verge of becoming as accepted as the cane or seeing eye dog as a navigation aid for the blind. This man's cane assists him to prevent tripping over on uneven surfaces. For navigation, he relies on CASPRA for a sonar view of the surroundings.
I had a problem with the experts in England, psychological experts, who felt that blind people would not be able to use the sonar I proposed. I found that bats seemed to use the sonar, and that gave me the confidence to go ahead in spite of the opposition from the psychological field. That opposition died once I had produced the result.
CASPRA is a headband which emits frequency-modulated ultrasound signals much like the bat. Two receptors a few inches apart in the headband produce stereo sounds in the earphones, like our eyes, which produce stereo visual images, giving us depth perception. The wearer, after a few training exercises, can react to the changes in pitch and tell the distance and dimensions of obstacles, even identifying individual objects.
I just walk past here, this mesh fence, and here's a tree right here, and walk around the corner, and there's a car, so we'll go around that too.
The tiny echoes received are converted into tones. The brain seems to be able to convert these sounds into a 3D picture, just as it does with eyesight. Sonar may soon enable the blind to see the outer world like sighted humans. And sonar is enabling sighted humans to see the inner world clearer than ever before.
Wild Tech.
Little baby Eve suffers from a rare heart abnormality, first diagnosed while she was still a fetus in her mother's womb.
In utero, the heart rate was between 200 and 300 beats per minute, and after birth was also still very high. So now with the medication, we've brought the heart rate down to a respectable nearly 100 beats per minute.
You'd be looking to bring that down any lower? Or
No, I'm very happy with a heart rate, that sort of heart rate for her at this stage. There's, bringing it too much lower will compromise her, so we should not try and bring it too much lower. She looks a good deal better than she did when I first met her.
She looks incredibly.
Dr. Robert Yates saved Eve's life by making an advanced diagnosis before she was born, using a machine that for the first time gives a detailed view of the organs of a fetus while it's developing deep in its mother's womb. It uses sound to see, much in the same way that dolphins have long taken for granted. Dolphins have an undisputed advantage over humans in their ability to see underwater, whether clear or murky. Dolphins have sonar, which gives them second sight using sound. Using pulse-like signals generated in the dolphin's nasal passages at frequencies beyond the range of human hearing, the sounds are transmitted through the dolphin's head and reflect off objects in the water. These acoustic echoes then bounce back and are received through the dolphin's lower jaw and transmitted to its brain. The signal is transformed by the brain into a visual image. Dave Goodson is from the Underwater Acoustics Group at Loughborough University in England.
The dolphin is primarily looking for food. He's looking for fish, and he's looking for something he can swallow whole. So there's a limit to the upper size of target he's looking for. And he would be initially searching with a click repetition rate. He produces these pulses every 1/10 of a second. And when he detects a target, he will start to speed up the pulse repetition rate so that as soon as he receives the echo from the target, he fires the next pulse. So as he swims closer to the animal, the click rate gets faster.
The dolphin's sonar works in a similar way to an ultrasound machine. The machine chirps and listens for echoes. But where dolphins use frequencies just outside human hearing, the ultrasound machines use weaker signals at much higher frequencies.
The back of the baby here, the front of the baby.
Up until recently, the technology has only been able to produce two-dimensional imaging.
See the baby's tummy here.
While these are detailed, they fall short of a dolphin's three-dimensional sonar capabilities.
You can see the baby's moving around, it's moving its arms around, and the baby takes its hands away from the front of its chest.
Helena is now 17 weeks pregnant, and while she's feeling healthy, Dr. Yates is concerned her unborn baby may have fetal heart problems.
When we look at the baby's chest here, we can compare the size of the chest and the size of the baby's heart to the markers down the side of the screen here. And on the screen, each of these individual little white marks represents 1 centimetre. If we compare that to the size of the baby's heart at this gestation, then the baby's heart is little more than 1 centimetre from apex to base. So we're imaging a structure that is not much bigger than 1 centimetre in its entire length, and magnifying it considerably to be able to display it on the screen.
Using a common 2D ultrasound machine, Dr. Yates examines the flat image of the fetal heart. Correct diagnosis is limited, as he can only approximate the workings of the heart chambers of the unborn baby. A dolphin sonar doesn't rely on approximations to get a full picture. Evolution has given it an extra dimension.
Just to put it into perspective, a bottlenose dolphin can see something the size of an orange about 80 meters ahead of him. And that is approximately equivalent to the echo it would get from quite a large fish, but one that it could still swallow whole. So we've got a good feel, I think, for what they do in the wild when they're looking for fish mid-water. But then we discover the interesting things, like the dolphin who is looking into the seabed surface at close range and clearly has detected the presence of a fish that's buried in the sand. Now, the echoes at the frequencies they produce should bounce from the sand, but they're able to get some information from below the sand particles, and they will sometimes even dive into the sand to recover them.
The dolphin's capacity to see a hidden object in 3 dimensions using sonar is what Drs. Yates and his colleague Dr. Deng at the University College London are aiming to replicate using ultrasound. Clearly, a true 3D image would enable Dr. Yates to see the heart in action from whatever angle he chooses, and therefore make a more accurate diagnosis.
What we're going to try and do is time the cardiac cycle according to the output from the baby's heart, and we're doing that by using a second machine to measure the baby's heartbeat in the umbilical artery, and by timing the heartbeat according to the umbilical artery, we can then acquire a 3-dimensional image of the fetal heart, knowing at what point of the cardiac cycle the acquisition is taking place.
Around the world, the race is on to develop 3D ultrasound imaging machines. This team has developed a specialized technique synchronizing two traditional ultrasounds. By combining the data gained by the two machines and syncing it to a single heartbeat, sophisticated computer software creates a 3D image. This is cropped to delete unwanted information.
Lines here, and we can take those out with the cropping utility on the post-processing software of the machine, and then we can get to the bit of the fetal heart or the bit of the fetus that we want to.
Dr. Yates can now observe the actual motion of the baby's heart valves. The team has named the technology 4D ultrasound imaging.
The two collecting chambers, and you can see the two pumping chambers.
That's 3D imaging in real time.
So here's a three-dimensional picture of the fetal heart, which I think is, that's astounding technology, considering the size of this baby's heart is really very, very small. And we're able to see the wall between the two collecting chambers here, which in the fetus has a communication between it, and we can even see the communication between the two collecting chambers. And remembering what I said about the size of this fetal heart, you can see the motion of the valves between the collecting chambers and the pumping chambers. How's Eve today?
Seems to be much better.
Good.
She's been really quite settled today.
Has she had further episodes of tachycardia?
She's had a couple.
Right.
The potential for this technology is virtually unlimited. It should soon be possible with 3D and 4D to not only diagnose fetal abnormalities, but to also assess the exact treatment required, maybe even enable fetal heart surgery, and make the difference between life and death for babies just like little Eve. Seeing with sound. Seeing with heat. Flight using bee sight. The ability of technology to replicate the way nature sees has expanded our vision of ourselves, our world, and our universe. While human sight may be limited compared to nature's, it is our unlimited vision that makes us look to technology for our future insights.